about the latency and why it's the most important thing, the most important metric of your cloud. How many of you know who StorPool is? StorPool? Okay, very few, right? So first, my role in the company, I'm the chief of product, one of the founders. Cloud architect, meaning I help a lot of our customers who are cloud service providers build and design and kind of deploy cloud services. And my background used to be, I used to do kind of packet processing and kind of millions of packets per second on standard servers. And even before that, I used to kind of compete, do competitive programming, which is very interesting stuff if anyone of you knows that. What we do is a very kind of fast and efficient software-defined storage system. We deliver it as software and services on customers' servers in customers' data center. We started a long time ago in my youth, and it's a clean slate design. So it's not based on anything. It's our own design from scratch, and that makes it quite more capable and has a lot of kind of different capabilities to the storage systems you may be used to. Most of our deployments are with KVM, so even though we do have some deployments with VMware and Xen and Hyper-V, KVM is the most popular hypervisor among our customers, and we do have deep integrations into OpenStack and CloudStack and OpenAWS and ONAP, and also in Kubernetes. So we play a lot in this kind of Linux KVM stuff, right? So back to our kind of topic for today. Every transaction processing system, be that a load balancer, a web server, an application server, a database, a storage system, all of them have a performance characteristic that goes something like this. So you have like operations per second and average latency per operation. If you increase the operations per second, you also get slightly higher latency. So for example, one task on 4 cores takes 1 second, 2 tasks 1 second, 4 tasks still 1 second. So this is still kind of 1 second per task completed, right? Where this model breaks is when you get 6 tasks on 4 cores or more, and then it's not 6 tasks in kind of 1 second per task, it's 6 tasks at 1.5 seconds per task. So you didn't do more work, you just hit what we call a saturation point, and these systems tend to have 2 very different modes of operation. One we call it elastic mode, where you have more demand, you get more work done, and then in the congested mode, you get more demand, you don't get more work done. So in kind of your application where you want to run your systems to get kind of the best user experience, pages opening fast, etc., is in this part of the curve. So imagine you have all kinds of different systems, storage, databases, application servers, all kinds of systems, message queues. You want to run them at that part of the curve. Well, you wouldn't run them like some of your systems, you would run higher in the curve because it's more cost efficient. But the problem with running them close to the knee, close to the saturation point, is that the moment you go over the saturation point, it's only pain. Only pain means kind of operations piling up, kind of stuff piling up in queues, and you don't get just slightly higher latency, you get infinite latency. So kind of really long queues that the system is trying to push through slowly. So this characteristic of the system, how high the saturation point is, you can call that the throughput of the system in some metric, right? So most of system vendors, storage vendors, database vendors, they like to brag about how many operations per second their system can do. Most cloud operators, when they sell you virtual disk, they tell you this virtual disk has this many IOPS. But in reality, like for the performance of your application, this doesn't matter at all. Like what matters is how that system behaves in the part of this curve where you're going to use it. So it doesn't matter how high the line is, right? It only matters like how low the latency is for the number of operations per second that you're going to put on that system. Well, with one exception. So the only reason you care about system throughput is that you don't want to get into the situation of going over the system throughput and kind of exceeding the system throughput, right? So a system that has 1 million IOPS helps you avoid going over the need, right? So the demo I've prepared is that I have two different storage systems, two different virtual disks. Both of them have 20,000 IOPS. Meaning, if I take kind of feel and measure how many IOPS per second both of these volumes have, they will both return, say, it's 20,000 IOPS per second. So both of them could be sold by, say, in one cloud or another cloud, and they will have the same specification of 20,000 IOPS per second. And I'll show that application performance will be very different on the two volumes, even though they're both 20,000 IOPS per second volumes. Right? So what we have is one virtual machine with 8 vCPUs and 16 gigs of RAM, a virtual disk with 20,000 IOPS per second, and a PostgreSQL database, which is 4 times the memory. It's a fairly small database, to be honest, like a 64 gigabyte database, and in large web applications, these databases would be kind of significantly larger than that. So it's not kind of a very extreme case. Can you guys see this, or should I make it bigger? Who doesn't see it? You don't see it. Okay. I'll try and make it slightly bigger then. Just 1 second. There we go. All right, so how do we show it's 20,000 IOPS per second? We're going to run this test on it, and this is not the latency test, sorry. This is a random reads and writes, 50% reads, 50% writes, with block size 4K and a large queue depth, so a lot of parallel operations, on a file which is on that virtual disk. And it didn't even get 20,000 IOPS per second. Second time. So this is the demo effect. So we can show that that volume does 20,000 IOPS per second. So 10,000 reads and 10,000 writes. Total 20,000. Okay. And pgbench is a benchmarking tool provided by PostgreSQL. The way we use it here is kind of completely following kind of the described test methodology by Postgre. It's not kind of a complete random benchmark that we wrote. It's an established benchmark. So what we do here is there are 16 clients in parallel on 8 threads. Why 8 threads? Because it has 8 vCPUs. We'll see progress every second, and kind of total benchmark time is 10 seconds. And what we can see here is kind of that with this many clients in parallel, this database can do, there's the kind of average transactions per second for the whole test. So that's, I'll try to bring that higher, let's do that a bit higher. So it's 1,400 transactions per second on this volume. So what this gives us, so the storage volume underneath has 20,000 IOPS. The database we put on top does 1,400 transactions per second. Okay. So if we ask our database to do, say, 1,500 transactions per second, what would happen is, so in this column here, log, this will, well, it didn't increase high enough, so let's try something slightly higher. So you have like a queue of operations piling up, and now database transactions are not taking a few milliseconds, they're taking 4 seconds and 5 seconds, and a few minutes later they will be taking a lot more. Because we are asking this database to do more than what it can do. Now, to switch to another volume, so what this does is kind of switches the storage underneath and restarts the database on the faster storage. That storage also, that's also a kind of 20,000, try a second time, 20,000 IOPS storage, you know, so 10,000 reads and 10,000 writes. And that database without the limit does about 3,000 transactions per second. So what we saw here is 2 virtual disks, both of them with 20,000 IOPS limit, right? So okay. But the database, with the same number of parallel clients, the database can do twice as many transactions per second. Which means that when you go to a public cloud operator and you buy a virtual disk with 10,000 IOPS provisioned on it, that doesn't tell you anything about the performance of the application you're going to get into. And kind of, it's the state of the industry and why I'm doing this talk, that we need to talk, like, when analyzing performance, we need to talk about kind of the elastic part of the curve. We don't need to talk, you know, that IOPS is interesting, but it's not where we run our applications, right? And same thing, so if we do RAID 1750, a database that can do 3,000 transactions per second, if we ask it to do 1,700 transactions per second, you'll obviously not get a pile up of operations. You get, you know, it's pretty happy processing these. Or something. All right, so, all right, okay. Moving on. So, we are in the process of kind of collecting interesting application benchmarks. So we think it's not well established that services which look identical on specification can be so different from each other. And what we did is, it's still in progress, but we started this process and we got virtual machines from a bunch of different public cloud operators and measured random reads and writes with QDepth1 on the different operators. In DigitalOcean, we got like about 2 milliseconds. In DreamHost, the Dream Compute service, we got about 5 milliseconds average latency for 4 kilobyte storage operations. Right. And so what do we learn from this? That, you know, DigitalOcean is very good at running Ceph, right? Their Ceph cluster is 3 times faster than everybody else's. You know, they've done a good job. The problem with this is that if you go to Amazon Web Services and you just buy, you know, EBS service from them, you get 0.3 milliseconds average latency, right? So it's not competitive. If I'm an application developer, I run my application on DigitalOcean, and I will outgrow DigitalOcean at some point, and I will move to AWS. Right? It's just not competitive at all with the market leaders. And like we also measured that in a kind of production StorPool cluster. This cluster specifically is running shared hosting services. It's about 80% full. Unfortunately, it's not a public cloud, but it's kind of a fairly well-loaded system. And we're going kind of trying to get a public cloud service in this, so you guys can try out the same thing. So I wonder, like, if there is 7 times difference in latency of the underlying storage system. So the way this test is designed, what it does is it tells us how far this end of the curve is from the beginning, right? So it doesn't describe the whole curve, it just tells where the starting point is. So if you have 7 times difference in that, what would be the difference in database performance or kind of application performance? And the difference is kind of night and day. So on digital ocean block storage, which is Ceph-based, you could get, like, if you have an application that needs, say, 500 transactions per second in a transactional database, you may run that on DigitalOcean and you'll get like 20 milliseconds latency for your transactions, right? But if you go to AWS, the same 500 transactions per second, you would get the same thing for 1.5 milliseconds average latency per transaction. Right? And also, just in case you have an application that needs 2,000 transactions per second, you cannot run that on DigitalOcean, but you can run that on AWS or a faster storage service, right? So the difference between these is kind of the DigitalOcean service is also limited at 10,000 IOPS per second, the same as the EBS volume. The only difference between the two is latency of storage operations. They're both 10K, 10,000 IOPS volumes, right? And I have a couple of minutes for questions. So if anyone, does anyone kind of want to stand up and defend Ceph? There are a lot of Ceph fans here, I'm sure. No. All right. Any questions? Sorry, I don't hear you.
What about Ceph running over RDMA? I heard a lot, haven't tried, but...
Right, so we're not experts in Ceph, our company, right? And we don't run Ceph clusters. And also, if we were running Ceph clusters, it would be considered bad benchmarking because no one trusts us to do Ceph well, right? So the best option is, if you have a Ceph cluster and you run Ceph with RDMA, we can run the same benchmarks on your cluster. I am extremely doubtful that will make any difference, right? Because I don't think these 5 milliseconds of latency are kind of the latency to transfer 4 kilobytes over a network, right? It's kind of somewhere else in the stack, it's not there.
RDMA allows to write directly to memory of another host. So
it does, but
performance is heavy.
So sending 4 kilobytes over TCP connection, does that take 5 milliseconds? I don't think it does.
It could send even 1 megabyte at one packet within.
It's not about throughput.
10 milliseconds.
So again, the difference between the systems is not both of these services. So the DigitalOcean service on this chart, the green one, and the Amazon EBS service, they're both limited to 10,000 IOPS per second. So it's not about, in this case, it's not about how many IOPS can the user.
It's not about IOPS, it's about latency.
Right.
Then,
so being able to send 1 megabyte over the network doesn't help this at all. It's just completely useless to help it.
Size of the package, like you need less amount of input-output operations at first. ability to write to memory gives you slightly lower tail.
It's very interesting and theoretical, and until I see
it's
it.
Theoretical.
Yeah. Until I run the same benchmarks on a system like that, I don't believe it.
I was curious if you have any
No. So, last thing on Ceph, we've heard these kind of performance has been a problem in Ceph for a very long time. We've heard these promises that we're going to fix it in next version and BlueStor is going to make it better, and now RDMA is going to make it better apparently. But it just never happens. It's just years and years and years, and it's not getting better.
BlueStor was released.
Yeah, BlueStor helps, but not enough. Okay, thank you. Let's take that offline because kind of I'm being kicked off stage here. My timer is done. Thank you guys.